And now we do a very exciting lesson about the atoms called the quantum mechanical model. In this lesson, we're going to learn about quanta, mechanics, models. It's the quantum mechanical model. So let's jump right in. Not too long ago, scientists knew very little about the atom, and so basically, our concept of an atom was something like this. We knew that there were atoms, but we didn't know anything about them. This is basically what John Dalton gave us. However, with a few experiments, we began to develop this model into something different. Remember, this model led us to a new model once we discovered the presence of these negatively charged substances. Is this starting to look like a chocolate chip cookie yet? Do you remember the model? This is J.J. Thomson's model. Now, he actually called it the plum pudding model, but in his model, he incorporated negative electrons within the positive material. And then a guy named Ernest Rutherford came along, and his experiment forced us to change that model again. Rutherford's model took all of the material of the atom and placed it in a little tiny center called the nucleus, and put the electrons way out on the outside of the atom, with lots of space but no material in between the nucleus and the electron. Another scientist named Niels Bohr did a better job of describing these electrons. He realized that the electrons were quantized. They had certain quantities of energy. And so he placed those electrons in something called an orbit, much like a planetary orbit. Remember from our past lesson, Bohr taught us that the electrons didn't have to stay in an orbit, that they could move in between orbits, and when they did, energy was either absorbed or released. Now that's a great model, and we'll still use that model, but it's not completely accurate. And this is what leads us to the new model. In the new model for the atom, we have a completely different concept for the placement of the electrons, though the name may sound similar. The name is called orbitals, not orbits, orbitals. What is an orbital, you say? Well, it's this region around the nucleus where you'll probably find an electron. You see, Bohr's model said that the electron moved around in an orbit, but that is not true. Electrons don't move in a predictable pattern like planets do as they orbit a nucleus. The best we can do is we can estimate where the electron likely would be. And that is the concept for an orbital. It's where the electron is most of the time. A couple other things that we need to understand about orbitals. First of all, they can hold a maximum of 2 electrons, but these electrons, if they're in an orbital, have opposite spin. And secondly, these orbitals come in 4 distinct shapes, and you ought to know about the shapes. The first one makes a lot of sense. It's called an s orbital, and it's spherical in shape. So the spherical orbital is the s orbital. The next one has more of a dumbbell shape and a name that doesn't match. It's called the p orbital. P for dumbbell. The next one is called a d orbital, and it kind of looks like a 4-leaf clover. The d orbital. The last orbital has a funky shape, so it is appropriately given the name f orbital, for the funky-shaped orbital. Now, let's complicate this a little bit, because it's not just an orbital that we're organizing here. You see, orbitals can be combined into sublevels. A sublevel is a series of orbitals that all have the same energy and the same basic shape. There are 4 types of sublevels. Now, don't zone out on me. I can see your eyes starting to gloss over. Listen, this part's pretty easy. The 4 types of sublevels have the same name as the 4 types of orbitals. The first sublevel is called an s sublevel, and I want you to note it is only made of 1 orbital, the s orbital. The next sublevel is called a p sublevel, appropriately named because it's made of p orbitals. However, I want you to notice that these p orbitals are arranged differently. Notice that the first p orbital, sometimes called the px orbital, sits on the x-axis, while the next one sits on the z-axis, and then finally there's one that sits on the y-axis. Together, these 3 p orbitals make up what we call a p sublevel. So let's see if you can guess What is the next sublevel going to be called? That's right, it's the d sublevel. And the d sublevel is made of 5 orbitals, arranged differently in space, but all having the same amount of energy. Now let's consider these d sublevels. They get a little more complicated when there's 5 different orientations. So together, these 5 different arrangements of d orbitals are combined into what we call a d sublevel. By now, you're probably on to me. So you can tell that the next sublevel is going to be named, that's right, the f sublevel, and it's going to contain how many different orbitals? 7 orbitals. Excellent. These are the 4 kinds of sublevels. Now let's see if you're still tracking with me. I wonder how many electrons can fit into this s orbital that's drawn up here. How many electrons fit in there? Well, 2 electrons fit into an orbital. I wonder how many electrons would fit in this p orbital. This one down here, a p orbital. That's right. It also holds 2 electrons. By the way, the electrons don't have to be in opposite sides of that p orbital. They could both be in the same side. So what about the d orbitals? I wonder how many electrons can fit in that orbital. No, not 4. This orbital also holds 2 electrons. Somewhere in that space, you could have up to 2 electrons. All right, hopefully you've figured this out. Take a look carefully at one of these funky shaped orbitals. How many electrons do you see fitting into an f orbital? That's right. 2 electrons fit in an orbital. Now, a check of your math skills. So, in a s sublevel, how many total electrons would fit? 2 electrons fit. Excellent. And what about the p sublevel? How many total electrons fit there? That's right, 6 electrons. 2 electrons in each orbital for a total of 6. In our next sublevel, the d sublevel, there's a capacity of 10 electrons. And finally, in the f sublevel, we have a maximum capacity of 14 electrons. And this is where electrons will arrange themselves around the atom. Keep in mind that at the very center of each of these drawings, at the origin of the coordinate system, that is where you would find protons and neutrons. Just to make sure you understand these, I'd like to show you one other picture. In this diagram, we have 3 spherical objects. I wonder what that first spherical object is. It kind of looks like an s orbital. And the second one, well, that looks like an s orbital, and so does the last picture. So what's the difference between these? Well, the first picture might represent the 1s orbital, the lowest energy orbital, whereas the second one would be a higher energy s orbital, and the third one even higher. So my point is, there are different sized orbitals that have different amounts of energy. So let's arrange some electrons in an atom. We're going to do that using an orbital energy diagram. This one will do. You'll notice that as you move up the diagram, you're also increasing in energy. So where on this diagram do you think the electrons would prefer to be? That's right, they'd prefer to be in the lowest energy. So if we had an atom with an electron, that electron would go down in the 1s sublevel. And if it had 2 electrons, we'd put them both in the 1s sublevel, because that is the lowest possible energy for those electrons. However, if there were 3 electrons, the next one would have to go at a higher energy level because there's no more room down in the first orbital. And so it would begin to fill in the 2s sublevel. What I'm doing right now actually has a name. It's called the Aufbau rule. And it says that sublevels are always filled from the lowest energy to the highest energy. And so we continue, as there are more and more electrons added, we continue to put electrons in the lowest available spot for them. You may have also noticed, while I'm filling in electrons, that I've done it in a specific way. The Pauli exclusion principle says that you can put a maximum of 2 electrons in each of these boxes. And if you do, you need to represent that they have opposite spin. We do that by putting the arrows pointing in opposite directions. As I continue on filling in electrons, my next electron will go in the 2p sublevel because that is the next lowest available sublevel. The next electron also would go in a 2p orbital, as would the next one. Notice the way that I arranged those. That might be kind of curious. Why didn't I put both electrons in the first box? Well, there's a rule for that too, and it's called Hund's rule. It says that each orbital in a sublevel should be half filled before you completely fill it. In other words, don't put 2 electrons in this first orbital if there's room in the other orbitals. I wonder why that would be. Well, you see, electrons are a bit antisocial. They don't like hanging out with other electrons in close spaces. Why is that? Why don't electrons like being around other electrons? Well, the answer is quite simple. Electrons have a negative charge, and if you try to put 2 negatively charged things too close together, they're going to be repelled. So it's not just that the electrons are antisocial, they're repulsed by other electrons. Now I've represented the first 10 electrons. Let's keep this diagram going. Sodium has 11 electrons. Its next electron would move up here to the 3s sublevel. And if we did magnesium, we would put the next electron in the next available sublevel. Some people over-apply this rule and they start moving the electrons up here and say, well, you know, I learned electrons don't like being around other electrons, so I'll just move them up here. That is true, electrons don't like being near each other, but to put electrons way up in this next energy level is just too costly. It takes too much energy. So even though they are antisocial and they don't want to be near other electrons, they will if it saves them from moving to the next higher energy sublevel. And on we go, filling in the electrons until we've got a spot for all of the electrons in our atom. So if you were representing a large atom like iron, you would keep drawing electrons all the way into the 3d sublevel. Now I'm going to stop here because I think you get the basic idea, and hopefully you learn these rules because we're going to use these rules as we continue to build on this concept of representing electrons.